Hello everyone, welcome to Learning Express YouTube channel. So today we'll continue with the CTQ 10 in the continuation of CTQ series. Previous videos we have completed the CTQ 9 from various angles. We have discussed the six circuits, possibly with the gain calculation, after that swing analysis, and later in detail the noise analysis. But in this problem, we'll see the two circuits are given and we have to compare the circuits based on their gain, swing, noise, and biasing. So these are the four things that I have mentioned here to compare the circuit based on these four. Rather, you can see something else also, which I have not mentioned maybe. So these two circuits comparison is required, and what possible parameters you can compare by your own, it's up to you. But I'll start with my discussion. Okay, so let me take one thing here. Let this current sources are ideal. Better to take the current sources ideal. Okay, so all IDs are ideal. All I naught are ideal current sources. Okay, so current sources are ideal. Now we'll see from the gain point of view. In the first circuit, what we can see, let me tell you one thing. Just take this as a your input one, and V in is input two. It means we are taking the differential input. Just a differential structure is there. So two differential inputs. Let's say for the signal point of view, it is V divided two. Then it will be minus V divided two. So we are feeding differential signal both the sides, and accordingly we have to see for the differential gain. That's it. Okay. So from gain point of view, what you can see. Okay, so from a small signal point of view, the first circuit will be what? This if these current sources are open circuit or the circuit is symmetric. So from that viewpoint, we can see both the circuits are similar. Okay, so if this current source you can consider as a open, but even this point will be virtual ground because the circuit is symmetric. So there is a no point of discussion that with this point is virtual ground or not. It's a virtual ground. Okay, so here this side also this point is again the virtual ground, so we can find again this is my v out 1, this is my v out 2, and so differential output is a v out 1 minus v out 2 we can find. And okay, as I told you, the current sources are ideal, so you can consider the infinite impedance for the current sources, and we can have this is the differential inputs, or I'll say this is my plus v in by 2 into minus by v in by 2. Of course, common mode is applied there. So from here we can find this v out is what? V out is my v out 1 minus v out 2, and again will be find from here. Okay, so what you can see, if there is a virtual short because the circuit is symmetric, both side there is a degeneration. Okay, so degeneration is happening here. Okay, so due to degeneration, what is the gain calculation? I'll not going to tell you what is the gain calculation for that. You can easily calculate, make it the half circuit and analyze it depending on that. Okay, so for the second circuit also you can see if that circuit is also symmetric, so it should also be same. Okay, so if I'll go with this circuit is also symmetric. So what we can see, this resistor, instead of 2R, we can split into R and R. Rest the circuit is symmetric. So there should not be any change in the gain. This is my V in 1, this is my V in 2. Okay, so these current sources are separately here. But as I told you, current sources are ideal. So no point of considering them. Okay, this is my V out 1, this is V out 2. So from the small signal point of view, this node will be virtual short. It is a virtual short. Virtual short, or I should say AC short node, because of symmetric structure. So this circuit is also same as the previous one. So what we can see from the gain point of view, there is a no difference in these two circuits. Okay, so from gain point of view, there is no difference. Okay, that's fine. You can calculate V out 1, V out 2. So differential voltage is my V out 1 minus V out 2 is my V out, and from here you can calculate the gain V out by V in. Okay, one side is positive input, other side is negative input. So we can calculate from here. So from gain point of view, both the circuits are same. I can put a note here. From small signal gain point of view, both the circuits are same. Both the circuits are. Now where the difference? Now we will see that where the difference when we will do the DC analysis here. Okay, from the DC viewpoint, just look from the DC viewpoint. So what is in the first circuit? I naught. This is my input 1, which is nothing but a common mode because I am considering a DC, and here R 2 I naught. We'll see something good here while we analyze the DC. V into, this is I naught, this is VDD. So what we can see from here, when we set the output common mode, or when we see the output swing, let I consider the output 1, then what you see, there is a flow of I naught here, there is a flow of I naught here. Okay, so let me consider the half circuit. You can see, or need not to consider half, but yeah, I can show you by considering half one thing, that there is a swing limitation in this circuit. What you will see, there is a degeneration is happening here. Of course, degeneration is important in AC, but here this I naught is flowing here. I can consider the circuit like this. V out. So if there is a common mode voltage, accordingly the I naught is flowing. So what you see here, the voltage is dropped. This voltage is what? Due to this I naught R, voltage is dropping across it. So what we can see, this transistor will take its own overdrive voltage, and some voltage drop across this resistor I naught R. So in DC, what we will see that V out can go as low as V overdrive plus I naught R. This V overdrive is important for the transistor, which is transistors on voltage, I will say, on voltage, to keep it in saturation. To keep it in saturation. So this is the required voltage. But unnecessarily we are losing some voltage due to this degeneration resistor. So from swing point of view, swing is limited. Okay, swing is limited. And also we can see due to the degeneration, what is happening, degeneration obviously is happening in the second circuit also, but I mean to say here in the circuit, the continuous flow of current across the resistor is also burning, or also wastage of power. So here is power wastage also. Okay, so continuously your I is flowing across the R. So this is the voltage that is dropping across the R. It is limiting the swing, and from here we can see power across the R is your I naught square R. So there is a heat dissipation also, I can say. Heat dissipation. So from DC point of view, we can see this resistor is not good when the current sources are connected like this. It means always there is a flow of I naught current across the resistors, so swing is limited. Also, this heat dissipation is there. Now look at the second circuit. What is happening here? Obviously, no problem. I naught we are running from upper side. This is my so from DC, what I can see, this is 2R. This current I naught is going down, but we can see one thing. We can see one thing. There is a no current is flowing across this 2R resistor. Okay, that we can see here. As the current is coming from the upper side I naught, and it is going down as a I naught, so there is a no flow in between. Okay, so these 2 points are equipotential point that I can say. Okay, These 2 points are equipotential points. From the symmetry we can see there is no current flow. 0 ampere current is flowing. So in DC condition, this circuit is better. This circuit is better because it is not limiting the swing. Rather, you can see one thing that in a DC condition there is a no current flowing across the 2R, so no extra heat dissipation. So no extra heat dissipation due to no heat dissipation is there. Also, we can see that in a DC point of view, what potential of this node is, there's just potential of this means potential across this current source, whatever this the potential is. Here we are considering the ideal current source. If this is the MOS current source, it will take some value of voltage here. That voltage plus this overdrive voltage is the voltage required here. Okay, but in the previous case, the extra voltage was going across this R, which was I naught R. Okay, rest there was some voltage due to this current source. So this voltage is extra, not a point here. But yeah, you can see the extra current, extra voltage of I naught R we were wasting there in the DC. So swing was less there. So from swing point of view and power dissipation, the second circuit is better. That we can see. Okay. So gain wise they are same, but DC wise second circuit is better. So we have seen these two circuits on the basis of one, what the DC uh, analysis, and basis on the DC analysis we have seen what are the biasing effects there, how these are involving in the power dissipation. So both the circuits are different in terms of DC, but the gain is same. From a swing point of view, you can also see, but the one thing that is left is a noise. From noise viewpoint we'll see this analysis in next video. Okay, so just I want to give the overview that what are this why I considered these two circuits. Just you can see and analyze and what are the possibilities while we are setting a bias point for the circuit. So while biasing there is obviously some difference there. From gain point of view both the circuits are same. So I think I should consider noise in the next session. Noise in next video. Okay. So thank you. This is enough for this video.